Good afternoon, sir.
Oh, same. Good afternoon. So, where are you now? At a university or?
No, sir, PG.
Oh, PG. Okay. So, yesterday, did you go? I mean, during this time to university these days?
No, sir,
Okay.
because no one was there. Only I am here. Others, they all went home.
Oh, okay. So, today I think we have only to go through Hall effect, and I think some Hall effect note I have also given you. So, let me check.
Yes, sir, you gave last day.
So, Hall effect in metals and semiconductors. Okay, so I think that is a topic in syllabus. Let me check once. The Hall effect in metals and semiconductors. Okay. So band theory, band gaps, band diagram, etc. I mean, the notes are, I mean, directly you can read from the book, the Puri and Babbar book. Okay. And the elementary band theory that you will learn when EK sir will teach you. So then this band theory, etc. I mean, in that case, I mean, after that, the band gaps, energy bands, although we have discussed, but those things will be more clear to you. Okay, Hall effect in metal and semiconductor, that we can discuss briefly today, and I think with that our syllabus will be over. And if later if you have some questions or like later means in future classes, like some doubt clear, some doubt has to be cleared, then we can discuss those things.
Sir,
Oh no, why am I sharing this? Not this one. All right. Okay, let's see if some more people join, then we can start. Or others, I think. I don't know whether they will join or not. Okay, I will download one Hall effect image and I will upload that to Google Classroom because the note is there, but some image have I given? No, no image. So image, let me go. Okay, so I think this image is very easy to understand when we talk about Hall effect. Okay, so it clearly shows the separation of charge carriers and current is flowing. The magnetic field is perpendicular to the conductor, and this Hall voltage, which is developed because of the separation of the charge carriers due to the magnetic field. So this Hall voltage is actually perpendicular to both the current and the magnetic field. Okay, both this current and the magnetic field. So I think this picture is quite easy to understand. So I am posting this picture to Google Classroom. Okay, so anyway, let us. No one has joined except you. So Hall effect in metals and semiconductors. So we have, I think, discussed this first page. What is Hall effect? How you define it? Then what are the applications of this Hall effect? Like you can determine what type of semiconductor it is. It is p-type or n-type. Okay. P-type means holes are majority carriers and n-type means electrons are majority carriers. Then determination of carrier density. So carrier density is small n. Okay, small n I think you have also calculated for your practical. So carrier density that can be calculated for a given semiconductor material. Like for your practical case, you have calculated that of germanium. Okay. So this Hall effect thing, it is also required in MSc classes. So when you will go to MSc and MSc class, so I think in second semester at USTM at second semester MSc, we again teach this Hall effect. So these things will be very easy for you to capture. I mean, easy for you to understand if you understand now properly. But maybe in MSc level, you have to go more into the mathematical part. Okay, so determination of carrier mobility. Okay, carrier mobility also you can calculate. Mobility is mobility formulas. I don't remember exactly. The formulas are given in most of the textbooks. So measurement of magnetic field. Magnetic field also you can do magnetic field calculation. Then measurement of power in an electromagnetic field. Okay, so this thing also you can do. Although this measurement of power in magnetic in an electromagnetic wave, this is not required right now, maybe in some other classes. So anyway, these are some of the applications of Hall effect. So Hall effect is very important topic in semiconductor physics. Okay. So now Hall effect in metals and semiconductors, it is given in your book, and here we have some small some mathematical steps, but these are not very detailed mathematical derivation or like that, just some steps. We imagine that the charge carriers, so I hope you will be able to understand the handwriting. So handwriting, I don't know, it's not, it does not seem too good, but I hope you will be able to understand. So just a moment. Yeah. So we imagine that the charge carriers move in a medium that offers some resistance. Okay, in a metal generally, in a metal or in a semiconductor, whenever charge carriers move, they always encounter, they always get resistance. Resistance means they collide with ions or they collide with impurities in the material concerned, be it metal, be it semiconductor. The resistance is due to scattering between the carriers and the impurities in the material. Okay. The resistance is due to scattering between carrier and impurities in the material, and between carrier and in what did I write this one? And in cations. And what did I write it? Oh, vibration. Okay. So the resistance is due to scattering between the carriers and impurities. Okay. So if there are impurities in the material, so the carriers, the charge carriers, be electrons or holes, they will collide with the impurities. Okay. That's how also resistance occurs. Resistance is an opposition to the flow of electric current. Okay. As you know, the definition of resistance, even in your high school also you have learned about resistance. Okay. And the vibration of the material atoms. Okay, material atoms, when they vibrate due to high temperature and so on, so that also creates resistance. Okay, because vibration of atoms results in scattering with impurities. Each charge carrier is accelerated by the applied field. Okay, but so often it scatters and loses energy. Applied field means applied electric field. Okay, charge carriers are accelerated by applied electric field, but very often they are scattered by the impurities. Okay, and loss energy. What losses energy? The charge carriers. Okay, maybe I can do some small annotation here somewhere. Give me some time. Suppose this is your material, any conductor. So suppose I will give only, I will draw only one electron. Okay, suppose this is only one electron, because I cannot, in this limited space, I cannot draw so many electrons, too many electrons. So suppose there are impurities here and there. Okay. So what will happen? This electron, you can accelerate the electron with the help of applied field. Applied field means here we are talking about applied electric field. Okay, so the electron will gain some energy, it will gain energy, and it will be in motion. So the electron will collide with this atom. Okay, and what will happen because of this collision? The electron will change its direction. Maybe it will come here to this wall. Okay, so that the electron loses some energy. Again, maybe the electron will later collide with this particular impurity or ion, or there are actually many electrons and ions in the material concerned. Okay, not only one. Here we are showing only one. So this way there will be collision between electrons and ions, and this way, like, they will get some kind of resistance during their motion. Okay, this resistance or opposition, they will get some opposition during their motion, and that causes the resistance. Okay, and due to such scattering, they lose energy. Okay, if we assume that average time between scattering events is this tau. Okay, scattering, if average time means scattering between scattering of the electron between this impurity and this impurity. Suppose the average time is tau. Okay, then we have an average a retarding force. Okay, retarding force means opposing force. Okay, retarding force acting on the carriers of. So what is the retarding force? Opposite retarding force means when the electron collides with impurities, so the motion of the electron will be retarded, or the motion of the electron will be opposed. In such a case, the retarding force will be given by an equation like this. So F vector retard equal to minus mv divided by tau. Okay, so how this equation comes? It is very simple again. So what is force? Force is mass multiplied by acceleration. Okay, and mass is m. Suppose mass is the charge carrier, and acceleration is velocity by time. Okay, velocity means rate of change of velocity. Okay, so how much velocity is changing with respect to time. So you know already this equation, very famous, you already have learned. So but in this case, retarding force means the force acts in a direction opposite to the direction of motion of the charge carrier or the electron. So to be a bit precise, how we can write this expression for force? So since it is retarding or opposing force, so you have to include a negative sign, opposing force. M v vector divided by t. In place of t, we are what is our average time between two consecutive scattering events? That is tau. Okay, instead of a small t, we will write it as tau. That's it, nothing different. So that's the equation 1. Okay, so I hope you have understood now how equation 1 can be written. So m is the mass of the charge carrier. Okay, now under the influence of applied electric and magnetic field, Newton's second law becomes, so okay, so in Hall effect we have both electric and magnetic field are acting on the substance or on the material. Okay, so in that case the total force will have components of both electric and magnetic field, which is given by this m dv dt equal to q e plus v vector cross b vector. Okay, so this is the Lorentz force, we all know this first quantity. So total force, this is the total force. Okay, m dv dt, this is the Lorentz force minus this retardation force, f retard, that you have to, actually it should be plus. Okay, plus it. So total force is the Lorentz force plus this retardation force or retard force of retard. What is this called? Retarding force. Lorentz force plus retarding force. But Lorentz force is okay like this, and retarding force is a negative quantity, so we are using the negative symbol here directly. Okay, so that is the total force acting on the charge carriers. Okay, I hope you have understood this equation now. So total force, this is Lorentz force because of the presence of the both electric field and magnetic field, minus the retarding force because the electrons they will collide with the like impurities and ions, etc., and therefore there will be a force which will act opposite to the direction of the motion of the electron or whatever be the charge carrier, which results due to scattering between electron and impurity. Okay, so this is the equation. So equation for total force. So at steady state, the time derivative of v vector, okay, will vanish under time derivative of v vector. Okay, so this quantity will vanish. So under the usual convention, okay, this is, I have written convention. Under the usual convention that b vector points along the z-axis, we obtain the component equation for v vector by setting the left hand side of the equation to 0 and rearranging. Okay, we obtain the component equations for velocity, like velocity along, see, velocity is a vector quantity. Okay, so since it is a vector quantity, it will have both directions and magnitude. Okay, so direction means it will have directions along all x-axis, y-axis and z-axis. Okay, so but at the same time, at the steady state, this quantity, first quantity, will be equal to 0. Okay, b and obtain the, okay, so at the steady state the time derivative of v will vanish. Okay, that means this quantity will be 0. So ultimately this one will be equal to this one. Okay, so this Lorentz force will become equal to the retarding force. Okay, So and okay, on both sides you have to just like x components and y components. So you see, velocity will have all components x, y, z. Electric field is also a vector quantity, so it will also have ex, ey, ez components. Magnetic field will also have okay, magnetic field has only one component along the z axis, so magnetic field has only bz values. Okay, so actually some like earlier I did this simplification, and it is actually like this. Okay, so detail is not required. If possible, try to remember them. Okay, so remember we have three vector quantities. So electric field vector, velocity vector, and magnetic field vector. So magnetic field vector is, as it is assumed that magnetic field vector has only is directed only along the z axis. Okay, whereas it is not any, there is no preferential direction for electric field vector and velocity vector. Okay, so electric field and velocity vector all have like x, y, and z coordinates. Okay, velocity vectors bx, by, vz, electric field vector ex, ey, ez. Okay, and magnetic field only bz. Okay, so yeah, can I show you some simplification? It may be long, but anyway, so I will check this calculation later, because in this class, if we have to go this, it will take long time. If possible, I will do it separately and upload to Google Classroom. Okay, I mean this one, this from equation 2 to equation 3, considering steady state. Steady state means this particular part m dv vector over dt will, actually dv vector over dt will be 0 at steady state, and this left hand side will be 0. Okay, okay, so from equation 1, what is equation 1? Okay, this is equation 1. We have jx equal to nq vx. Jx equal to nq vx. Okay, I don't know, I don't remember how from equation 1 directly this is coming. I have to see the main note. Okay, okay, just give me 2 minutes. I will see the main note. Just give me 2 minutes. Okay. Okay, I hope you can see this PDF document. Actually, I prepared this the Hall effect thing from this particular document. So background, etc. So here you see, in actually equation 1 is this one. So Ix equal to Jx omega t, or so Jx is nq Vx omega t, or otherwise Jx is equal to nq Vx. So actually this is the equation 1. Okay. And from here, Hall effect in metal and semiconductor, I hope you are able to see this. So this retarding force equation is actually equation 7. Okay. Since I did not include this part because this part is more quantitative in Hall effect, but you don't need the quantitative description. So I directly consider this retarding force equation to be equation 1. Okay. So so here they are correct in the note. So from equation 1 we have this. Okay. So for what I can say you is that you don't write from equation 1. So there may be some misunderstanding. From equation 1 you don't write, because equation 1 is something different in our note. So you write, we know that, you can directly write, we know that this Jx is equal to nq Vx. Okay, you can directly write like this. And then let me go to check the main note. Okay, then the next thing also is a bit mathematical, and that is written directly here. So here the current density terms, this Jx, Jy, Jz, these are actually current density terms. Okay, current density is current per unit cross section area. So this current density terms, by solving above equations for Vx, Vy and Vz in terms of components E vector and Bz, we have, so Jx is equal to like sigma. So sigma divided by this quantity 1 plus omega c tau whole square, then Ex plus omega c tau Ey. Then Jy sigma by again this quantity omega c tau whole square, Ey minus omega c tau Ex, and this Jz is equal to sigma Ez. Okay. So let me just quickly give you one information. So what is the relationship between this J vector? J stands for current density. J is equal to sigma. Sigma means conductivity, like resistance, resistivity, conductance, conductivity. Okay, conductivity is just the opposite of resistivity. So this J vector current density is can be written like this: sigma multiplied by electric field vector, or conductivity multiplied by electric field vector. Okay. So this J vector, so these are some simplified forms. So remembering this, if we have to remember this relation, then let me remove the annotation. So J vector is sigma. Sigma term will be there because it is a conductivity term, and current density is a vector quantity. Once again, current density is a vector quantity, just like velocity and electric field. Velocity and electric field, and also magnetic field is a vector quantity, but also remember current density is vector as well. So Jx is equal to sigma over 1 plus omega c tau square, and okay, it is written like this. If you can remember, it is better. Where sigma is conductivity, and sigma value is given by something like this: nq square tau divided by m. Okay, and omega c is this quantity, cyclotron frequency. So what is cyclotron frequency? It is not required. You don't you don't require it to know now. You can just this will be required in MSc, yeah, MSc, not MSc of MSc. Yeah, in MSc maybe you recur it MSc condensed matter physics class. Okay. So, but anyway, you remember that this is cyclotron frequency. So, what is cyclotron? Cyclotron is actually a accelerator. Okay. So, this accelerator, the frequency of a charge carrier in that cyclotron accelerator is generally represented by omega c. So, about cyclotron, those students who have condensed matter physics as special paper, so they have to learn this topic in details, a bit details, cyclotron frequency. Okay. So anyway, so you can just remember this for now, but details is not required. So omega c value is q bz divided by m. Okay, q is the charge. Okay, charge of an electron or any charge carrier. Maybe it is a hole also. So Bz is the magnetic field. Magnetic field is assumed to be only along the z axis, z direction, divided by m. M is the mass of the charge carrier. Okay, so these quantities, you have to remember: sigma conductivity, omega c cyclotron frequency. Okay, and this sigma and omega c, they come in the expressions for current density, Jx, Jy, Jz. Okay. Okay, the parameter tau is called relaxation time. Okay, relaxation time means like it is kind of like time between two consecutive scattering. Okay, so that we have already discussed. Yeah, the average time between scattering events, between two scattering events. Okay, scattering with one impurity and scattering with other impurity. Okay, then and omega c is a quantity known as cyclotron frequency. It is the frequency of rotation of a charge in a magnetic field and can be taken as a measure of strength of field. Okay, a cyclotron, of course, a magnetic field has to be there in order to move the charge through that accelerator. So it is the frequency of the charge in that particular accelerator when you also have to apply a magnetic field. Okay, of a charge in a magnetic field. Okay. So omega c tau. Now this little bit about this quantity omega c tau. The combination of omega c means again the cyclotron frequency, and tau stands for the relaxation time, is used to characterize an experimental situation. If the magnetic field is weak or the relaxation time is short, okay. If the magnetic field is weak or relaxation time is short, then omega c tau is much less than 1. Or our experiment is in weak field limit. Okay, weak field limit. So this omega c tau quantity we are talking about. So this omega c tau quantity, if magnetic field is weak or relaxation time is very short, then this omega c tau is much less than 1. Charge magnetic field. Let's see tau. Okay, tau, not only tau, but there is also this whole square time. And okay, it is called weak field limit. Alternately, if omega c tau is much greater than 1, the experiment is in the strong field limit. Strong field limit means that like the applied magnetic field is quite high. So weak field limit, weak field means weak magnetic field here, and strong field means strong magnetic field. Okay, and yeah, so two conditions: omega c tau, if it is much less than 1, it is in weak magnetic field; much greater than 1, then that is in the strong magnetic field. Okay. Okay, anyway, so that was some Hall effect in metals and semiconductors. So a little bit mathematical. So here it's okay. So this retardation force, then total force, and how this Vx, Vy, Vz are coming. I will try to show you separately in a different calculation. And this one it is not actually equation 1, because the equation 1 is actually from the original note. In the original note, it is written from equation 1. So that one you can write Jx is equal to nq Vx. Okay, that like that you can write. And yeah, so correspondingly, how we can write this Jx, Jy, Jz quantities. These Jx, Jy, Jz are current densities. Okay, and current density is also a vector quantity, so it has three components: Jx, Jy, Jz. And just this bracket terms you try to remember. Okay, so this denominator terms are equal, so 1 plus whole square, this whole square, they are equal, but just try to play around with the bracket terms. Okay, parameter tau is relaxation time, and yeah, omega c tau, if it is much less than 1, it is in the weak magnetic field, and if omega c tau is much greater than 1, then that is the strong magnetic field or strong field limit. Okay, so that's all about Hall effect in metals and semiconductors. So I think I should also give you that original document of Hall effect in metals and semiconductors. So that one also you can go through, the same one which I showed you. Give me some time. Can I just drag it here? Maybe I can drag it. So, yeah, dragging works. Okay, so the Hall effect, so it is the original document from which I made this note, this handwritten note. So that one also I have added to Google Classroom, and you can go through it. Okay, so I think that's all. That's all about Hall effect, also qualitative discussion, so not much mathematical derivation, etc. And Hall effect, one good thing is you also learn about this thing in your practical classes. So your concept about this topic should be very good, actually, about Hall effect. Okay. Okay. So from next class, you have any question? From
No, sir.
next class? Huh?
Uh, First, we'll see the notes. Then, if there is some
Okay.
problem, we'll ask.
So yeah, and also the Puri and Babbar book is in Google Classroom. You can also the videos, the uploaded videos you can watch, and Puri and Babbar book is there. Most of the things I have done from that book. So notes, handwritten notes, I have not given you. So whatever things I have taught you are from the book. So you can, or just 1 minute. So I have one Google Classroom for MSc second semester. Just a minute. So maybe I can add all of you in that Google Classroom. Email. I don't know how I can add. Because there you can find some notes. Okay. But those notes in that MSc class, they are written from other sources, not from the Puri and Babbar book. But still, maybe you find something. So another classroom, something useful. Let me check if I can add you. Let me check. Okay, I mean, what I will do is I will copy the class link. Okay, I have copied the class
So, if you
link.
give us the link, we can join individually.
Oh, okay. Let me give you the code then. Let me give you the code for this
Yes, sir.
class. Okay. Okay, I remember the code. It is 5 CNR, 5 capital, no, sorry, it's 5 CNR, all in small, then PYJ, 5 CNR, PYJ. So you can see maybe, I think you can also see it here. Yeah,
Mm-hmm.
this one. So using this code, you can join this MSc second sem physics USTM. So here there are many notes last year classwork. If I go to classwork section, there are many notes related to your course also and some other topics. But these notes are written from other books mostly, not from this Korean Babbar book, but from other sources. So you can go through whatever you think will be useful for you. You can make note on that. Okay. Okay. I think
Okay, sir.
I will stop the sharing. Okay. So I hope you have noted down the link to the Google Classroom. It is once again 5 CNR PYJ. The chat
Yes,
box.
sir.
Yes, 5 CNR PYJ. Okay. So okay, in the chat box I have written. So you can note it down, and there you go through. Like if you need some notes, you can. A few things are like in given in more description there, but overall same thing, almost similar thing. We can say 60 to 70% similar to the notes or the content there. Okay. Okay. So I am ending the class.